70 and now 80. And it's been a pleasure, and they've all been extremely interesting and very different, if I may say so. This meeting seems to have a very toric flavor, and that reflects the fact that Sam is an extremely active mathematician. And all I can say is that we all hope that when we reach 80, we'll be as active and as lucid as he is. Now, of course, I have known Sam for many years, I guess because of family connections. As you all know, my uncle and he worked together for many years. They were the pair of famous topologists in Mexico that kind of started the game going here. And we all owe Sam a great debt of gratitude for what he's done in building Mexican mathematics. So I won't talk about toric topology here, but there will be a torus appearing here. So should I give some pre-calculus notes, the pre-lecture notes following Tony? So let me start out with just with a motivation. So suppose that G is, say, a Lie group. Let's say a compact Lie group for a minute. And a few years ago, Fred and I started looking at the following construction. We started looking at elements in G which commute pairwise. This sits naturally inside the Cartesian product. And we started looking at these guys. Well, the first thing you notice is that this is really a space of homomorphism. So we take the three abelian group. And it has it's a nice subspace. Bigger, okay. Okay, I'll try. And now one of the key factors which we noticed is that these spaces are rather complicated. And to continue the theme of splittings, oh, bigger than that, okay, sorry. Let me illustrate this by a stable splitting that Fred and I wrote down in a paper a few years ago. And it goes as follows. Let me introduce an auxiliary space, Ck twiddle of G is going to be equal to Ck of G modulo the commuting tuples, ordered commuting K tuples with at least one entry equal to 1. We divide out by that subspace, and we have the following. Yeah, so Ck, it's this thing over here, n equal K. The ordered commuting n tuples. You take the ordered commuting K tuples and you divide out those which have at least one entry equal to 1. Notice, for example, that the entry, the 1s in all the entries equal to 3. So there's a very nice splitting, which is very much in the spirit of the splittings that have been mentioned here. There's a good place to mention these. So we have the following splitting. We take the suspension of Cn of G. This is homotopy equivalent. A nice little formula like that. So what that's telling you then is that if you want to understand the homology of these commuting n tuples, then you have to understand the homology of all these pieces which go into the formula. Let me illustrate how bad that gets by looking at a particular example. And this is just about the only example we can compute completely. That's G equals SU2. In that case, these ingredients to the following. So Well, for k equals 1, it's just SU2. And for k bigger than 2, bigger than equal to 2, it's going to be equal to a Tom space. You take RP2, you take k times the line bundle, and you divide out by the section, 0 section. So, yes? Well, it's just a 1, right? 1 is a 1, you're making a 1 equal to a 1. So just SU2. Okay. So this is, the upshot here is that this has a bunch of 2 torsions. This is quite complicated. And in general, if you try to compute these commuting n-tuples, you'll find that the homology will have torsion at the order, at primes dividing the order of the violence. So these are varieties which have some very complicated torsion coming in. You see, in the case of SU2, you get a bunch of 2 torsion coming in, all these different factors. This decomposes. Oh, RP2, you take the Tom space of k times the line bundle, the line bundle, and then you divide out by the 0 section. This is the Tom space. This is Tom space. Tom space. That bundle. Can you divide out by the 0? The 0 section. 0 section of the bundle. 0 section of the bundle. Smash it down. Yeah. Okay. Now, so that's a motivation that tells you that these spaces can be rather complicated. So what do we do then with them? Well, we do what algebraic topologists like to do. We say, well, why do we consider these one at a time? Why don't we consider them all simultaneously, all at the same time, and put them into one big space? Can you read this? It's not readable? Can we make it bigger? Can we make it bigger? Where's our text? Okay. So, so we start out with any topological group, okay, and consider all these commuting n-tuples. Okay? So we take the collection of these order commuting n-tuples, and what we're going to do is assemble these. Oh, there. Look at that slide. Should I point it that way? I guess this doesn't show up there. And what you're going to do is assemble these into a simplicial space. So we consider these, the nth term of this simplicial space, and we're going to call B comm of G. It's going to be precisely these ordered commuting n-tuples contained in the Cartesian product and topologized that way. And here we assume that G is a topological group, and let's assume that the identity element is a non-degenerate base point. And, yes? Okay. There we go. That's a lot better. Just go down? Okay. What does this do? Okay. Okay. So, okay. So then we assemble these into a simplicial space, and the observation here is that the face and degeneracy maps are defined in the classical way, just as you do in the usual model for the bar construction. You take the face and degeneracy map, and the observation is that these work perfectly well for the commuting element. I guess I don't have control over that. Yeah. You can scroll down. You can stop there. Okay. Yeah. Now the different SJs and delta Js are well defined and satisfy the simplicial identities, as these maps are precisely the restrictions of the degeneracy and face maps in the bar construction. And so now we're taking them all at the same time, and we put them into this simplicial space. And what we can do is take the geometric realization of this simplicial space. And that's a space we're going to call B comm of G. Similarly, we can take, let the first variable be a free variable, put G in there, and we can define E comm of G, and this will define a simplicial space E comm of G star with its geometric realization, which we will call E comm of G for the purposes of this talk. Now this definition, wait, momento. Well, the thing is that the things are defined in terms of homomorphism, right? So this is like a natural construction to the ionization of the free group. And now this construction was introduced in a paper that I wrote with Fred and with a former student of mine, Enrique Torres. Okay, so now how does this relate to what we've been talking about here? Well, if you take this space Bcom of G, and you take its filtration, the standard filtration in this realization, then this is homotopy equivalent to the Kate suspension of so these terms here are appearing when you take the filtration quotient of the geometric realization. This marker is dead. Okay. So I should say that parenthetically that I did actually write a paper with Sam, with Martin, with Tony, and with Fred, where we talked about splittings. Raise your hand, maybe you're a co-author. Yeah, and where we did splittings of simplicial spaces with a strong co-vibration property. We kind of have a unified view of many of these splittings. Okay, so now the point of this talk then is to try to understand some things about the topology of these spaces. Okay, maybe we'll, at least I think that is. The first thing we observe is that unlike for the case of the standard construction, the EG and the BG, things here are a little bit different. You could consider the case of a finite group, for example. Say G is finite. Oh, that's good. G finite. And you might consider this guy Ecom. Ecom G. So this Ecom G is in over Bcom G. And here we have the usual universal bundle. And we can think of this as pulling back. We have the natural match going like this. Okay. So this is the general case. Now for G finite, you might wonder, so here this space is contractible, right? And this is the K pi 1 in the case of G finite. Well, it turns out that for G finite, this construction gives you some very interesting spaces with all sorts of kinds of properties. For example, you have that Ecom of A5 has the homotopy type of a wedge of 854 circles. This is a provocative example. One conjecture that Fred and I and Enrique made was, or conjecture or question we asked, is Bcom G a K pi 1 for G finite? These are functorial constructions, and if for some reason we can get a space which is not a K pi 1, but that would be a little bit interesting. And it turns out that they are not K pi 1s. This does not hold. And in fact, there's an example given by a student of mine, OK, behind OK. He shows that for the extra special 2 group of order 32, which is the central product of B8 with Q8, order B32, he shows that the homotopy groups of B com G are equal to G cross E2 for I equals 1. And you'll get the homotopy groups of a wedge of 151 two-spheres. So that's that has an interesting combinatorics. And of course, the modules which you get here in the cohomology of this Ecom G, they're very interesting representations. But here in this talk, we want to focus in on the case of Lie groups. And the first thing we want to observe or we're going to assume here, is that these spaces are path connected for all n greater than or equal to 0. So this is a technical assumption we want to make for the purposes of this presentation. Now that'll hold for finite Cartesian products of these classical groups, SUR, UQ, and SQ. However, all these constructions would go forward with simplicial models, simplicial constructions at the component of the identity. You could do all of this, restrict to the component of the identity, and you'd get a Bcom G bar 1, which means it's the component of the identity, and same thing, you get an Ecom G at that But for our purposes, let's focus in on this special case. And the key hypothesis there for those groups is that the maximal abelian subgroups are connected. Now, when topologists consider Lie groups, we always restrict to compact Lie groups because for us, we have the Iwasawa decomposition or Gram-Schmidt or whatever. We can restrict to the maximal compact subgroup. So the first step here to reduce to maximal compact subgroups is a result actually proved recently by a couple of colleagues of mine. At my instigation, they wrote a paper that is going to appear in the journal in Geometry and Topology, where they prove that, in fact, the commuting K-tuples for a Lie group, for, in fact, the real or complex reductive algebraic group, have the same homotopy type as that of a maximal compact subgroup. And that's a complicated result because you have to be looking at commuting matrices and doing this all simultaneously. So it's rather an effort. But we can plug in their results to prove the following, that the natural inclusion map, if you have a real or complex reductive algebraic group with maximal compact subgroup K, then the inclusion map induces homotopy equivalences between B com K, B com G, E com of K, and E com of G. So we can then say, okay, let's focus in on compact subgroups. Yo digo, ¿dónde parar? Ahí está bien. Perfect. So now, there are only 7 slides, by the way, so don't despair. Then I say, well, we're in compact situation. So how can we describe this in terms of tractable, a tractable kind of model for homotopy theorists? Well, what we do is use the maximal tori. So in this sense, the tori are appearing in our lecture. So we take the topological poset, tau of G, constructed using the maximal tori and their intersection. And now you can see that there's a natural identification of B com G with the co-limit of the classifying space of the tori, or this category. So all the maximal tori and their intersection. Now the first basic result with inclusion, right? And then of course it's a topological one. Yeah, it has a topology itself, right? And it has an order by inclusion. It has a topology and it has the order by inclusion, just strictly by inclusion. And no. Yeah, so there's a topology on the object and on the ordered. They have this order, and that's like a closed subspace of the pairs. And then you have morphisms that have to preserve order. Okay. So right now we're assuming that everything is in a maximal torus. Otherwise, we would be looking at the component of the identity. We're looking at something like UN. Maximal tori and their intersection. Just that. No ON. We're not doing ON. We have that standing assumption here that that these things are all path connected, and the standing assumption here will be products of SUNs, UNs, and vectors. Okay, so the first observation is that the co-limit is homotopy equivalent to the homotopy co-limit. Again, this is follows from the fact that you have this nice cofibration. And similarly, you can show that E com of G is homotopy equivalent to the homotopy co-limit of these flags. So, in fact, you can recover this one from this by applying the Borel. So that gives you a model for computing what these spaces look like. Now, here's an example of computation. So, in fact, you can reduce these homotopy co-limits to a calculation over a discrete category. I don't want to get into the details, but you can actually simplify these descriptions quite a bit. So let's look again at the case of SU2. So this is a Lie group of rank 1. In this case, the poset, D of G, has one element corresponding to the center of G, which is isomorphic to Z mod 2. This has rank 0, and an element for every maximal torus in G. Okay? Now fix T and G, the maximal torus consisting of those 2 by 2 diagonal matrices in G. In the Weil group, G2 acts by permutation of the diagonal entry. So the space of all maximal tori in G is homeomorphic to G modulo the normalizer, right? And therefore, these are the objects here. 0 points, this is the special guy, and then RP2. Now in this case, you can reduce, as I said, to a discrete category. You'll have a RP infinity, this bundle, here you take S2 cross CP infinity, you divide out by a diagonal action of Z2. And here you just have the product of RP2 cross RP infinity. And B column of G in this case is homotopy equivalent to the homotopy push out of this diagram. Un poquito más para ver este último pedazo. So it's a homotopy push out of this diagram. You compute that, and you get the following calculation for the cohomology. So the cohomology is going to be a Z in 0. It'll be 0 if K is equal to 2 or K is odd. Z plus Z if K is congruent to 0 mod 4, K greater than 0. And you'll have a Z mod 2 if K is greater than, if K is congruent to 2 mod 4. So you see then that BSU2 is, of course, I guess, HP infinity. So it has this Z in degrees congruent to 0 mod 4. And you see that, we will see that you can actually see that fitting in there. One of these classes actually comes from that. Because remember that we have a natural map from BCom of G to BG. So in cohomology, we have a map from the cohomology of BG to the cohomology of BCom. So if everything is good, you should be able to somehow capture the cohomology of BG. But what's interesting is that there are other classes. So there's another class here in degree 4, which is actually an exterior class, which then goes along for a ride with the polynomial class forever. And there's this class here, which don't have a good explanation for it. The calculations over the integers are very complicated in this game. Producing cohomology classes with these Myers-Torres diagrams or these homotopy pushouts can be rather complicated. No. We know it rationally. We know everything, but for here, maybe we have to work harder. But okay. Now the next thing we looked into was, well, what are these spaces? What does BCom of G play in terms of bundles? So playing around with the definition, we came out with the following result here. So it's a classifying space for bundles which are transitionally commutative. And what does that mean? Well, let G be the let Q be the classifying map for a principal G bundle over a finite W complex X. Then up to homotopy, Q factors through BCom G if and only if there's an open cover of X by elementary neighborhoods, in other words, where there's a trivialization, such that at intersections, the transition functions commute when they are simultaneously defined. So when it makes sense, they all commute. So, talking to like folks like Jack Morava and people like that, they say this is related to some issues in physics, but that's not totally clear to me. But one can play this game. You can define a notion of equivalence between transitionally commutative vector bundles, define some version of commutative K theory, and then we say, well, we're topologists, we're not afraid of limits, or co-limits. Let's take n to infinity and see what happens. What does BCom U say? And we have the following theorem. I think, okay, we gave it away. All right, anyway, the theorem here is that Z cross BCom U is in fact a loop space. And for any finite W complex X, there's a natural isomorphism of groups between this commutative K theory and homotopy classes of maps from X into Z cross BCom of U. And one can compute the K-com of the sphere is the same as our ordinary K theory, and these are complex K theory, M up to 3, but for S4, you get an extra element there. Now, when we did this, we said, we have like a manuscript up on the archive, and he said, well, this is a loop space, so the way you prove it's a loop space is by looking at these guys, using the usual sort of machinery. You look at that, you make that into a monoid using the block multiplication of matrices. So if you do something like this, things behave well with respect to commutativity. So if you apply the usual stuff of Graham-Siegel and do some stuff or whatever from the old days, you get that it's a loop space. So then in that paper we posed the question, well, is it possibly an infinite loop space? And it's in our attempts to prove it was an infinite loop space, it resisted the usual attempts, getting the operad axiom, the usual ones, and the Peter May-Siegel approach, the standard. However, last week, I had Ulrike Tillman visiting, so I put her in an office with our paper, and she thought about this, and they started playing around with it, and as of, the past 2 days ago, I think we are ready to say that this, in fact, is a nucleus. And the idea is that you want to extend the morphisms, you want to fatten your category to make it a permutative category. So instead of just doing inclusions of these for the tori, you throw in action of the symmetric group by permutations of the tori, like with the wild group. So if you do that, you'll get a permutative category, and that's all waiting to be written down and so forth. But it's kind of interesting, or / exciting. You'll get something like these guys. So you can define then an action of the symmetric group. And you can then take the homotopy group completion of this guy, and then what you'll get is something like this. This guy. And this guy actually fibers over and the fiber. And this is a map of infinite loop spaces, so then the fiber is an infinite loop space. There's another way of doing this, we're told, by using the action of a linear isometries operand, which is something which I don't exactly know so much about. But there's more than one way of proving it. So it's an infinite loop space and has some interesting problems. Okay. So, we'll go on to what's next. Well, now you have a nice space, and we'd like to compute the cohomology. Now we're convinced that it's important in bundle theory. So what can you say about its cohomology? Well, by looking at homotopy colimit module and computation for SU2, we expect these spaces to have rather intricate torsions, okay? So let us focus then on calculations for the rational cohomology. And inverting the order of the Weil group would suffice, but for purposes of this talk, we'll work over the rationals. Okay, so the first thing you note is that if we look at this map from B com G to BG, which is a classifying map for this principal G bundle, then it induces a monomorphism in rational cohomology. So that map I wrote down there, it's a monomorphism, it's injective, and the cohomology of B com G is free infinitely generated as a module over this cohomology. If this is the ideal generated by this image, then in fact you can write E com of G as this cohomology ring modulo that idea. So if you want a simple application of the Eilenberg-Morse. So you say, well, let's apply this and see what we can get. Now, we have the following observation that was made in the paper that Fred, Enrique, and I wrote. If you look at E com G, you can compute it as the cohomology of G mod T tensor the cohomology of BT with the diagonal action of W. W is the value. So it's acting diagonally. So for those that aren't so familiar with this theory, G mod T has an action of the Weil group, and its cohomology will contain all the irreducible representations of W. They're all spread out. This is all even dimensional. They're all spread out in some way, and all we know at the bottom, you get the trivial module. It's all spread out in a certain way. So what you're doing here is taking all the representations spread out and centering them with the cohomology of the maximal torus. And we know that the action of the Weil group here, if I cover this part up and just consider this part here, I'd be getting just the cohomology of BG, right? The classical computation you bore up. So from this, if you combine these two statements, you get the following. Let G denote a compact connected Lie group with maximal torus C and associated Weil group W. Then the cohomology of ecom G is in fact just the invariance of the tensor product of G mod T with itself. So you take two copies of this guy and you multiply. So then this is a problem then in invariant theory. The first thing you observe, finite dimensional, and what you're dealing with now in the case of the unitary groups aren't symmetric invariants, they're multi-symmetric invariants. They have two variables that symmetrize simultaneously. Now these are things which we've seen before. Well, some of us have seen before in the cohomology of the symmetric groups in terms of these detection theorems that go back to Madsen and Milgram and Nakalpa. Now you notice here that if G is a compact connected Lie group, then ecom G is contractible if and only if G is diffusible. So it's really measuring the obedience of that situation. Okay, now we're going to use the theory. We're going to use the theory of multisymmetric polynomials. So for the students in the audience, once you get to a situation which is kind of algebraic, then algebraists work very hard to compute. You can go there, go into the literature. There'll be huge numbers of papers on everything you can imagine about actions of groups and invariants, et cetera. They may not prove what you want, but you can contort and move around, and you're in good shape. And in this case, you can apply algebra. So this would be the analog of what the topologists did when they computed the cohomology of the cohomology of VUN, the classical calculation. And this is rationally, you compute it as the cohomology of the maximal torus and the invariance under the symmetric. And these are just the symmetric invariants. Very beautiful classical group. So now we have a two variable version of it. Now it gets a little bit complicated. They have invariants to deal with it. So you define the major index for any permutation as the sum of the i's, the value of this permutation in I is bigger than the value in I plus 1. And then remember that UN and GLN are the same to us because of that theorem I said. So now the Poncare, this is the Poncare series, driven at T here. This represents the Poncare series for ecom UN. And it's simply the sum of T to 2 times the major index of W plus the major index of W to the minus 1, and the sum over all elements in the symmetry. And of course, by what we said, that it's free and finitely generated over the cohomology of BUN, then when you take the Poncare series for Bcom of UN, all you have to do is divide out by the classes that represent the term. So that's the Poncare series. So that gives you a complete calculation then for the rational cohomology. Now, we want to take limits. And you get a very nice result there. Take limits, you obtain the following. The rational cohomology algebras, Bcom U, Bcom SU, and Bcom ST, are in fact polynomial algebras of counting. And here's an example. For example, Bcom U. It's a polynomial algebra on generator Z of A comma B. This is indexed over integers where B is greater than 0. These are polynomial generators. So at every finite stage, there are relations. So that kind of reminds you, as I was saying about the symmetric groups. The symmetric groups say at the prime 2. If I look at this guy, then that's polynomial. then if I go to a finite symmetric group, never false. There's some relations which creep in, and it's a similar situation. Now, yeah, I'm looking at it. And the degree is 2a. So I guess one would like to try to understand things about the cohomology at a prime, and also try to elucidate whether this infinite loop space structure, which is a new thing, whether you can use that to say things about the homotopy groups of these spaces and more things about their geometric role. I think that's the last slide. That's it. Thank you very much.
For the speaker.
Homology to be done. Like in the symmetric groups, right? Then they have this Nakaoka thing, and then kind of identifying it in terms of the algebraic generator, so like the business of Mui and all these guys with the Dixon invariant, right? So there's a game we played that in terms of multi-symmetric.
And one other question: when you were writing the thing in terms of co-limits, or were they homotopy co-limits or
they're co-limits to begin with, and you show you model that with homotopy. That doesn't apply here because we're restricting it just to groups where all the spaces of homomorphisms of commutative intervals were path connected. So as something like SO3, there's a whole bunch of components there.
What do you mean?
I made the blanket assumption, right, that all these spaces of commutative intervals were path connected for all n. And that's certainly not true for the SONs and things like that. In that case, you have to handle the component of the identity. And there are analogous constructions, but then it gets more delicate.
You show that you're using the result of multisymmetric function.
Yes.
Could you show me what kind of result of the theory you're using?
Well,
what kind of result of theory of multisymmetric function do you use?
Well, they have like a basis for generators. They kind of describe them. There's some people in Italy.
Yes, they generated by elementary multisymmetric function. What's the next?
They write those, right? There's certain relations, right? Then what you do is take a limit, right? And when you get to the limit, you see that you have a polynomial.
Yes. But if we go to the limit.
Yeah, go to the limit. But in the finite stage, you have very complicated relations.
Yes, exactly what we have result of this. With Elmaris, we consider this relation.
Okay.
But you mentioned exactly the limit.
Yes.
Thank you.
Witten asks
Oh yeah, that's right. Okay, yeah. So that was one of the motivations was a paper, a memoir written by Morgan, Borel, and Friedman, where they were considering the commuting pairs and triples in a compact Lie group. And the point there is that you want to consider the maps from the torus, the principal guys, and the what's it called? This connection, space of connections, right? Associated to principal D bundle for the torus, in particular for n equals to 3. And Witten had some statement saying that if your Lie group was such and such, I think it was the simplex, the spin groups, then the number it was path connected or something like that. Space of homomorphism of commuting elements was path connected. And there was some work by Koch and Smilga where they show that in fact C3, I believe, of this is not path connected for n equals to 7. So this is related to these questions that the physicists were looking in terms of these bundles and connections. So I think Witten started asking those questions to Borel. And of course, the pairs, they have some classical results. And they understand the geometry of these spaces. They also use the notion of almost commuting elements. did look at that, and I think we feel that Fred can say more, but we're really applying more of the methods of algebraic topology and commutative theory, right? That we've had success in a different direction from there. Well, just today I have an email saying that BUQ should be an infinite. Yeah, that one, yeah. So we did, I think this was the BU2, right? In our notation. The BUQ, I think I should work with these two. Yeah, there's a whole filtration associated to the descending central series of the free group. You have all these terms which filter BG. I just chose the commuting ones because those are like, well, we don't totally understand them, right? The other one, we're still working on the splittings and other aspects of them, but they're interesting for other people.
We have time for the questions.
Time for the photos.
Okay, so thank you very much, Alex. So next is the photo. Su atención, les informamos que la fotografía será tomada en el patio donde están los árboles, patio 1. Please, the photo has been taken at patio number 1, where are the trees. Thank you.